let me ask you for beginning. I speak at the conference from time to time, and the question is, how many of you attended the similar talk at previous conference? Is there anyone? Okay, quite a few people. The key question, what are you doing right now here? Why you decided to attend it again? And the good thing is that I have to revamp most of the content of the old talk, and now there are a lot of new content. So you should not regret about it. My name is Mikhail Khludnev. I'm with Grid Dynamics. We are helping retailer companies to build a scalable e-commerce platform to provide the great search experience for their visitors. We help them analyze data. We have wide DevOps practice and has a great experience in comprehensive cloud deployments. Here's the slide about me. My professional focus is e-commerce search. Since summer, I became a solar committer, which I'm really pleased about. And I already committed several JIRAs, and it was pretty much fun, especially when you have to fix after commit. You have to watch CI. It's pretty funny experience. My favorite pieces of functionality is joins, facets, and data import, for sure. My colleagues and myself post into our corporate blog about Lucene, and I have G+, so add me to your circles. So now we're going to talk about Lucene internals, and it backed much on the classic algorithms from information retrieval. And we start from Lucene Essentials, which, by the way, we can skip if you wish. Then we've looked into core Lucene classes. And then we've looked how Lucene execute a special type of query, conjunction query, where all clauses are mandatory. And then we pay much attention to one of the edge cases of such queries, about heavy conjunction queries. That's pretty important to many business applications and was recently improved in Lucene. So how many of you are aware about this data structure? So I think we can skip it for a while, right? OK, you're welcome. So it's just slides from Wikipedia. And how many of you knows about scorers? OK. Quite a few people. So scorer, just simple thing, is just an iterator over postings list in Lucene. So you should be aware about it. OK, and here's the old Scorers API. So Scorers is an iterator, but Scorer itself, it extends an iterator, but adds a method for getting the score for the current document. And let's look how all Lucene queries are built internally. So let's learn Lucene queries internals. It's quite a huge diagram, and we will look into it part by part. So Lucene provides a layer of abstract classes. So we have abstract Lucene query, which works like a factory for abstract weight. And weight in their order is factory for scorers. And here we have a recent change in Lucene core. We have bulk scorers introduced quite a few some time ago. And the purpose of bulk scorer is to start to organize process of the search. So coordinate search, and we will look into these details a little bit later. But the key thing here is that scorer encapsulates the most of the query logic. So it decides which documents will be retrieved by this query and how they will be scored. So the scorer is the most important part of the query implementation. And here is example of the concrete Lucene query. It's pretty key thing in Lucene is a term query, the query which you use when you search for the particular term. For example, you use this type of query when you search all documents which has field color with value red. And you can see the term query extends abstract query and creates own weight class, and the weight class creates own term scorer. And the term scorer implements all necessary logic. And you can see that term scorer uses the postings enumerator. It's a lower level data structure which it obtains from index reader. That's how every Lucene query is built in general. Here's the whole picture. And let's look into what's happened is in bulk scorer. So as well as scorer is an iterator, we should have somewhere some loop which works like iterator consumer. So here what's exactly happened there. So it just looped through the scorer and obtained the score for the current document. But of course, instead of printing something to the console, bulk scorer pushes the found document into collector and also supplies score over there. That is about bulk scorer. So let's look into key participants of the query execution. We have index searcher. Index searcher is quite an important thing of Lucene. It's the entry point for submitting search requests. So it has method search. It obtains query and collector. Query retrieves some documents, scores them, and pushes them into collector. And collector crops the top results for the results page, something like this. And of course, index searcher uses index reader to read index files. Nothing special here. Okay, let's zoom this diagram in. Here we have what we already saw. Index searcher starts executing query from requesting weight from the given query. And then sort of magic happens. So as you know, Lucene index is separated to autonomous segments. That's why search literally executed like looping through these segments and repeating search on the every segments again and again. Okay, let's put it so. So that's why after weight is created, index searcher start looping segments, and for every segment, it requests weight to create scorer, but not scorer, but bulk scorer. And the bulk scorer should access plain scorer to execute search. That's why weight create bulk scorer and they create plain scorer. And it worth to mention that the bulk scorer class mostly reused across all queries because there is nothing special in this loop. That's why most of queries use the same class and they create own scorer implementation. Then for the every segment, it creates, it requests collector to create leaf collector. And the leaf collector is a special collector delegate which collects results only from the single segment to allow merge them back into the main collector. It's a new change in Lucene core. It's just reasonable refactoring. And then after we have a scorer created for the certain segment and leaf collector for this segment, we can start searching on this segment by calling score from the bulk scorer. And here is the key thing happens. Bulk scorer loops plain scorer for the next documents again and again, and pushes every given every returned document number into collector. And it's up to collector to request score for the current document from the scorer. And here you can spot the pretty good flexibility because sometimes this certain kind of collector doesn't need score at all, and it's up to collector, and it can execute query without obtaining score information. So we have like opportunity for optimizing all this routine. And here's the whole picture, if you wish. Okay, now let's look into particular type of query, onto conjunction query. Conjunction query is pretty neat thing. It contains of several subclauses or subordinate query clauses and requires all subqueries as mandatory. So to match this conjunction query, document should has all these terms, all these given terms. So the executing this query starts from the creating scorers and putting these iterators into beginning. And then on the every step, we should try to position all these scorers onto the document with the maximum number from the current documents. It's quite cumbersome explanation, but now it will be clear. So from this picture, we can see that document number 0 and document number 1 doesn't match this query because these certain terms are absent. Yep. And then now we try to move all scores to the document number 2. So, by the way, why document 0 and document number 1 doesn't match this query? From this picture, how you can get this? Yeah, because term A is absent and document number 0 and document number 1. That's why we can consider document number 2 as a match candidate, and we can try to move all scores to the document number 2. It happens for this positing list, but when we try to move these scores to the document number 2, it's absent, and it just jump over it to the document number 3. Now it's clear that document number 2 also doesn't match this query, and we need to continue our process from an attempt to move all scores to the document number 3, like this. And when we are lucky to move all scores to the certain document, we can push it as a result into collector and assign some score, so we don't care really much about following details. But you spot the, you can see the key algorithms here when one scorer tries to advance another scorer, but it jumps over it. And this process is called by leapfrog, quite a funny process. It's funny and it's efficient. But now we are going to look in more complicated case, into heavy leapfrog. And it's quite hard to find the proper picture, the best one which I could find. So let's look into the same scorers, but in a little bit different way. So what we are starting from here? So what's the first operation in this with these scorers? What is the first step of this algorithm? What we move first? So here we have two posting lists, and what will be the first step of this algorithm? So will we move first scorer or second scorer? Which one? Second. So we should move second. Where should we move it? Where? 5, right? But the first scorer will try to advance second scorer to the document number 3. So it gives like called like advance 3, and reasonably it leapfrog to the document number 5. So it's clear why it advanced to the document number 5, because document number 3 and 4 are absent in the second posting list. But it's not clear how it could do that without enumerating document number 1 and number 2. And just believe me, and for example, I have an evidence that it shouldn't, that it did not enumerate document number 1 and number 2. So can you tell me how it's happened that we can pass to document number 5 without enumerating intermediate documents? How it's possible? skip list. Who's Alan? Oh, Alan. How are you? Aren't you bored about all this stuff? Okay. So it's a skip list, and why it's important. Alan, can you tell us why it's not possible with binary search? Because this seems like it can be done with binary search, because it's just in ascending sequence. So it should be quite well advanceable with binary search. What's your point? Sorry?
I can't remember.
Okay. Despite it looks like regular structure, which is quite applicable for binary search, it doesn't work there because underneath format of the posting list is quite comprehensive and quite complex because it uses some sort of complex compression. So it's not possible to jump over posting list without additional metadata. And this metadata is stored in skip list, which is written alongside every posting list. So in addition to posting list, we already have a skip list which accomplished the posting list. So we have another layer of indexes in Lucene index. And this data structure allows to advance through posting list with the huge chunks quite efficiently without enumerating intermediate documents. So it's pretty cool and efficient algorithms. That's why intersection in Lucene works pretty fast. And then we repeat this process again and again, but here we're quite close to our problem, to the heavy leapfrog problem. So once a day we run intersection between these two scorers, but what we see that when first scorer tries to advance second scorers, surprisingly, it takes some time. So we see in profiler or in the debugger that there is some looping happens inside. So it spends the computational resources for something which we cannot really understand. So what we do, we look deeper inside with profiler or with debugger and what we can see underneath. So it occurs, it turns out that internally inside of the second scorer, there is some other scorer or posting list which has many candidate documents, and our second scorer has sort of predicate which is shown by question mark over there. And when we try to move second scorer, it has to enumerate all candidate documents and check these candidate documents for the given predicate. So evaluate some sort of condition over these candidate documents. That's why this might take some time. So we have to enumerate all these candidates and check them for predicate until we found document where the predicate comply, until document comply to the predicate. Where we can meet this situation, it may happen quite often, and especially in the older version of Lucene, and it should happen rarely if you run current version of Lucene. So it might happen to all forms of queries which cares about term positions, with spatial queries, with functional ranges, with older implementation of mean should match, and partially even with current implementation of mean should match. And for example, do you know how to search over field which is not indexed but has doc values enabled? So do you know how to write the Solr query which will search on this field? Your answer is F. Can you do it a little bit simpler without cumbersome F-range syntaxes? Sorry, what? Okay, it's interesting, but even in this case, where we do not create inverted index for this field, we can search on this field just with plain term query syntaxes. And the index schema figure out that this field doesn't have inverted index build, and it creates special form query, which is quite close to functional range query, and will fully scan this doc values column and check every element for the given value. So it's a pretty cool feature and quite amazing. And the last case is a custom query. So most times when we create custom query with special retrieval logic, we might hit this problem of heavy leapfrog. So I want to skip this slide, which explains why it can happen to spatial queries. So we can come back to it if we really need, but here's the solution. So how we can solve this problem of heavy leapfrog when we have underneath candidate documents. We need just explicitly expose these posting list and execute this intersection in two phases. So in first phase, we intersect the given scorer and candidate documents, and only for those documents which passes the first phases of the intersection, we invoke the predicate. So we have to invoke predicate. We have to verify document number 1 because it's not possible to avoid this computation. So we have to check it for the correctness, but we can avoid to evaluating document number 3. Which we did before. So if you remember the previous approach, we evaluated predicate for the document number 3, and that's exactly the place where we waste our computational resources. And here, with two-phase verification approach, we can avoid this waste. So, but we still need to do it with document number 4 and number 5 until we found fully matched document. Document. We have 2 implementations of this approach so far. Sure.
Can you go back to the slide? Why 0 and 6?
Sorry, what?
So you said you used the first do the filtering, right? So why 0 and 6 is the result?
Why 0 and 6 in my result?
The third.
0 and the 6.
Yeah,
Why 0 and 6 drawn here? Why 0, 5, and 6 drawn here?
Suppose because the first only have 1 to 5. Actually, I don't really know.
Can we just come back to this later? It might be not the best picture. So Lucene, hold on, solar pulse filters is available for a couple of years already, so it solved a lot of practical problems, but the lack of flexibility or design beauty, let's put it so. And now we have a two-phase iterator approach available in the core Lucene, which is pretty great, and now we're going to look it deeply and how it works. We already saw this collaboration. The bulk scorer calls next doc from scorer and pushes the obtained document number into leaf collector, and collector requests score for every current document from the scorer. But now scorer has document S, has method S two-phase iterator, and this method allows you to adapt scorer to the two-phase iterator. And two-phase iterator is a special interface which consists of it holds two phases of matching, two phases of document verification. So the first phase provided as an iterator with method approximation. So, and the approximation is what I call candidates. So we have a gap in terminology, but now after it's happened, after adapting scorer to two-phase iterator happen, bulk scorer now should loop approximation for the document. So the searching starts from the first phase of searching occurs with approximation. And only for certain documents which passed another stages of intersection with enclosing scorers or something like that, only for certain of them, bulk scorer can call two-phase iterator for the second phase of searching. So it can ask two-phase iterator to confirm only certain of documents. And here is a way how we avoid unnecessary waste of computation for checking every document from approximation, something like this. But there are two subtle moments in this collaboration. That the first one is that leaf collector still requests score from the scorer, and that means that scorer should keep track of the iteration happens in approximation iterator. So to be able to properly compute score, but otherwise it's not possible. So it's quite a little bit tricky, I say. And another problem is that now the scorer should provide both like interfaces. So it should work like a plain scorer, but also it should be able to adapt to the two-phase iterator. And you can imagine how it can be implemented. You should put if statements inside of the code, which is not quite maintainable, convenient. That's why all scorers which provide two-phase iterator, they're built like two-phase iterator from the beginning, and has sort of wrapper to wrap two-phase iterator back to the plain scorer interface when they're requested for the providing old iterator API. That makes things more complicated and pretty funny to debug. Okay, I should say something about creating own custom queries. Now we have composite verify query, which is pretty good starting point for create such efficient queries. So composite verify query resides in spatial package, but nevertheless you can use it even you work with comprehensive linguistic or retrieval model. So it obtains a query for candidate documents or like approximation, and then it obtains predicate in form of value source. And the Boolean value method calls as a confirmation method for second phase of iteration. So you can write this class and just put your logic into this query and this predicate, but you also can just look inside, get the idea about it, or just steal some key things key pieces of the code of this implementation. That's pretty useful point to start to understand all this stuff. Let's summarize this section. Now all this implementation become quite more complex. You know, like every scorer should be able to be wrapped in unwrapped as a two-phase iterator. So if query combines several subqueries, it should be aware that some of them can be two-phase iterator, but other ones are not, and it should always adjust own logic and do crazy stuff. So we can check new implementation of Boolean query and understand how complex it became right now. And don't consider two-phase iteration as a like silver bullet. So it works, it optimizes intersection only in this certain case when you intersect this heavy query with a highly selective query, for example, with category filter, or like for example, you have heavy spatial query and you intersect it with a highly selective keyword query and something like that. But if the heavy query is the only query which you can search on, so two-phase iterator doesn't help you because you have to enumerate all candidate documents. So it's not silver bullet. It's just fixing all issue in the core Lucene algorithms. And just the curious fact that Solr functional range is not two-phase iterator yet, but Lucene functional range query is two-phase iterator. And that is. Okay, that's all about two-phase iterator. And as a summary, I want to show two ideas, like overall ideas about Lucene implementation. So these are two aims which Lucene always tries to achieve. So it tries to be really efficient and spend computation only for things which is useful for you. So it's try to avoid full scan as much as possible. And here's what two-phase iterator has been implemented. That's what we avoided with two-phase iterator. We don't need to loop many candidate documents anymore. We didn't touch memory efficiency, but you can believe me that Lucene is quite modest in memory consumption, and you actually can get it if you see that we have to process results from subqueries in a stream manner. We should process them iterating one by one instead of materializing all results from one subquery and then just combine results in memory. So Lucene doesn't do so to reduce memory consumption, and it makes it quite scalable and reliable information retrieval library. Of course, in real life, there are certain edge cases which makes all things not so cute as these formulas, but you know, Lucene tries so hard and achieve it in most cases. And we reached the last slide of my talk. Here's my favorite recent improvements in Lucene. We looked into bulk scorer and leaf collector. We've talked about two-phase iterator pretty much, but we also have several guys left Lucene code base. Out of order scoring has gone because it made all scoring, retrieval, and collecting logic quite cumbersome and comprehensive, so it was really inconvenient to have out of order scoring as a special case. But honestly, we lose some performance in some certain rare cases, but nevertheless, it's a good for Lucene health. Let's put it so. We also left funny named class, which was Boolean scorer 2. Now it was broken into several pieces and wisely named. So that's also positive. And there is a multi-stage, quite complex refactoring of removing filters and turning filtering into scoreless querying. It's almost over. And I think last JIRAs are still committing, and in next release, we will now have filters as a separate abstraction in Lucene core, which is pretty good thing because we used to have filtering and querying as like two separate cases, and they copy-paste most of the parts of the logic because filtering is just conjunction. Now we don't have them. It's pretty cool. That's all from me, and I'm open to your questions. Thanks for attending. That's all. So go ahead.
So now, actually, for these doc values, if
Doc values?
the doc values, if the indexing doc values format is faster with this two-phase.
Right, two-phase iteration make intersection of the doc values query with plain query much faster. So searching by this field is expensive because you need to scan all values. But now if you have, for example, category filter, it can leapfrog that heavy query much faster, and you have to compare the fewer values for the given value. That is. So two-phase iterator helps with these type of queries. Is there any questions?
Which awareness solar you start using this
There was many JIRAs. It was like long-lasting effort. I think it started to arrive from 5.1 maybe, and is still come in little parts on every release. But I think now it's mostly stable and there is not much work in it. I've heard about plans to make a min-should-match query is more efficient by applying two-phase iteration on it. But it's pretty complex problem from my point of view.
So that version 410 doesn't have this two-phase iteration?
No, it doesn't have. Even 5.0 doesn't have two-phase iterator yet. Anything else? It's clear? So, it's okay. Thank you.